Okay. So let's think where we are. We've taken a look at measurements, everything that we could think about, solids, liquids, gases, all the things that we could measure. We then thought about, well, this isn't going to work, is it? All the things that could go wrong with those measurements. The random errors, the systematic errors, the biases, where they come from. Talked a lot about just stuff that could go wrong, and that your systematic errors come from poor experiment design or poor handling of the tools, and the randomness is just random. It's random. It's human. It's not always human though. There's things like that we didn't talk about. The electricity supply is mostly constant, but then occasionally, hey, there's a spike in the electricity. And if your detector is detecting something and it's going along really, really, really fine, and then it gets a spike, and this is a random anomaly. How do I know that that's not real? If my spectra that includes real stuff, how do I know that that's not real? How do we make errors become either more apparent or less important? This is the spectrum that has been given, that you have recorded. Right now, you think, oh, that's interesting. Wasn't expecting that. Let's spend a month trying to figure out what that is. Yeah. But it's not real. So how do you go about determining that it isn't real?
Can you just look at what's possible? Like,
no, because the impossible is where science lives. I was writing an article over the weekend, and I was trying to explain how science works, that it is lots and lots of small improvements in what we know, followed by a great big explosion of something where somebody finds something that is completely crazy, completely unexpected, and then we take a shift, and everybody looks at that and builds that one out. So you can't just say, I don't believe you. Although that's part of what we're going to start doing today.
how about you do the experiment that you just started again?
How about you do it again? And this time the random event doesn't happen, but the real event does. Duplication, reproduction. Reproducibility is one of the absolute keys to all of scientific thinking. And so you do it again. You do it again. Randomness. Averages to, what did I do with all my new pens? I brought a whole bunch of new pens. And they're all, take a bunch of random numbers and average them. What do you get?
An average. Oh, random numbers and averages.
Bearing in mind, if the number is truly random, it will be both positive and negative in possibility. Randomness averages to 0. So if I take these two items and I add them together, I diminish the impact of the first one, and I reinforce the real data. Because the real numbers add, but random numbers, when you add them together, they just make the cells go away. Yeah. So if that was a random error, we would make it be visible, and then we would diminish its importance by just doing multiple sets of the experiment. So when you do a titration, you do that once. I mean, in general chemistry 1, you kind of did titration and then just went, I've worked really hard to get here. I think I'm gonna take the afternoon off. Yeah. No. In the real world, you do one titration to give you a ballpark of where the answer is my final volume between 25 and 28 milliliters of added acid. And then you do another one where you find the endpoint precisely. And then you do another one until it agrees with the first number. You do it until you get agreement. And if your third one doesn't agree with the second one, then you do it again until the fourth one agrees with the third one, or the fourth one agrees with the second one. And you do it until you have agreement in numbers. There's a lab that we're going to be doing called, we'll do a fractional precipitation, and then we'll have a solid, and we'll measure the mass of the solid. Do you weigh it once? No. You weigh it, and then you put it in the oven, and you dry it.
Oh, yeah.
And then you take it out of the oven, and then you weigh it again.
Oh, yeah.
No, you wait until it's at room temperature, because you can't weigh anything that's hotter than room temperature. Why? We talked about that, right?
Evaporation.
Because, actually I did this in chemistry 1 last week. If this is your balance, and I put a hot object on it, that object is hot and it's emanating heat. That heat goes to the environment, and the environment is made of gas. So those gases now catch thermals and they move. And when they move, they bring new cold air in, and you've got an air current. And one of the things that we talked about not having when you take the mass of a solid was no air currents. Because when you blow over the surface of the balance, it reads the wrong number. Yeah, so we're going to do a precipitation. We're going to get a solid, we're going to put it in the oven, dry it so that we know that we're measuring only the mass of the solid, not the mass of the solvent that it came from. And then we're going to weigh it until constant mass. The two numbers agree with each other. What if this is balance number 1, and this is balance number 2, and you put your object on here and it weighs X, and you put your object on here and it weighs a different mass. What if this one wasn't zeroed out correctly? and that when the balance is empty, it's reading the wrong value. Okay. Is that a random error? No, it's a systematic error. So I avoid systematic errors two ways. One way is that for the experiment that I have chosen, I keep the instrumentation, the measuring devices that I start with. I use the glassware that I start with. I use the balance that I start with. There's a whole bunch of burettes in the room. I use the burette that I start with. Okay? You stay consistent with the methodology that you have picked. If you switch midway, and there is a systematic error, now you have something that is off your trend line. Okay? Because let's say this is an experiment where you have a solid and it evaporates or reacts and goes into the gas phase or whatever. So we would have, if we're plotting mass versus time, we'd have a trend that looks like this. Well, the trend from this material is exactly the same. It's exactly the same. Except, well, not exactly, except this one is higher up than that one. If you overlay these two on top of each other, the trend is the same. So if all we were doing is find the slope of this graph, I wasn't concerned with the y-intercept. All I was finding is the slope. Then my systematic error doesn't really count here. But if I'm looking for y equals mx plus b, and I need the intercept, this intercept is wrong, that intercept is right. Okay. If I mixed and matched these two balances, assuming that they were both exactly identical, and instead of that data point, I had this data point. Now the computer doesn't put the line through those four data points. It puts them somewhere here. So just be consistent. I suspect that my experiment contains a systematic error, a bias. How do I test it? It's exactly what you would do. You would do the experiment again, but you'd do it with different equipment. Or better still, ask somebody else to do it. And that's how you identify, is there an error there? What kind of error is it? How, once we identify them, we can minimize their impact. We can live with the fact that your data no longer on the board is reading the wrong values, because we can go in and just say we found the error after we collected all the data. And now we're going to slide all these numbers down. You can do that. Or you repeat your whole data. Depends what you're doing. If you're doing something as simple as counting pennies, then you just do the whole experiment again. If you are doing something that involves growing trees and then cutting the trees down and counting something on the inside of the tree, then you've got a 15-year experiment. You can't just do it again. You have to now manipulate your data. Do you want some more pennies?
No.
I'm just making sure you're not trying to tell us something, Dr. Moore.
Because I was thinking of getting some more.
Oh.
some more from the 1940s? Just so that we have the spread.
That was disappointing, the 20 cents.
It's okay.
Okay, time to start talking about numbers. Yeah. Let's talk about precision and accuracy. So we had a look at this previously. This is a volumetric flask, and it says things like, hey, at 20 degrees Celsius, this TC will contain 250 milliliters plus or minus 0.12 milliliters. Whereas our non-volumetric general glass says, can you catch that in the light? 500 milliliters plus or minus 5%. What's 5% of 500? 25 milliliters. 25 milliliters
That's a good chunk.
plus or minus. So it could either be 25 milliliters more or 25 milliliters less. So, that's 50 milliliter uncertainty. So what we've been calling errors, when we get them to be numbers, we can continue to call them errors. The mathematical symbol that we use in our calculations is E. It's a lowercase e for error. But we're also going to call them uncertainties. Okay. I think I'm going to have to run and get some pens.
I have some beer leaves in there for me.
Everybody's favorite thing. Significant figures. All numbers are significant except one. 0. 0 is only significant some of the time.
Yeah.
Okay. So the deal with significant figures that I was talking to a student at the weekend. He's in high school, he's taking AP chemistry. He's one weekend and all his chemistry teacher has talked about is significant figures. This is not how we gain more scientists. The message here is brace yourself because chemistry is going to be boring. That's not the message from chemistry. Chemistry is the cool science. Okay, so the only thing that you have to worry about is in significant figures is look for the zeros. And there are only two cases. It's either significant or they're not. Are those zeros between two numbers? If the 0 is between two numbers, then you count it. All it means by significant figure is this a digit of precision that I include in my analysis? And if the 0 is between two numbers, then you count it. Is it behind a number and there's a decimal point? behind a number and there's a decimal point, then you also count it. Okay? These are the ones where the zeros are significant. And these right here, this list is everything that is not significant, which is everything else. Okay, so let's play. How many significant figures are there in the number 4? 4 is a number. It's a non-zero number. We lived quite well for thousands of years without the zero. Then somebody invented the zero and we went, oh, now I know how many sheep are not in that field. They didn't realize that they needed it. How many have I improved the precision of my number by adding a second digit? No. No. There's a zero here, and it is not between two numbers, and it is not behind a number, and there is no decimal point. So, what I'm going to do is add the decimal point. There's a zero and a decimal point, but the zero is not behind the number. How many significant figures now? Still one, because there is a zero, it is behind a number. It's not between two numbers, it's behind a number, but there's no decimal point. So if I put the decimal point, how many do I have now? The decimal validates all of the numbers behind the real number. That can't be there unless somebody measured it. So I went from 1 to 3. How, isn't there supposed to be a 2 somewhere in the middle? There's this ugly thing that is that. That decimal point validates this 0, but says, I do not know what my next number here is going to be. It could be a 9. It could be a 1. It could be a 0. It could be a 3. I don't know. I have no certainty what that number is. So my precision ends here. All of them count. That 0 counts because it is sandwiched between two numbers. There's a decimal with the 0 after a real number that validates all of that. That gets to be 5 numbers. We don't need more. That's it. Okay? You only have to worry about the zeros because a number like 4,000 only has one point of precision. If I wanted to let you know that I really knew that it was 4,000 and not 4,000-ish, I would have to put the dot there. Okay? All right. precision is often quoted as being the reproducibility of a number. I see it slightly differently. I see it as being, it's the amount of data that's in your answer. If we ask what time it is, and I say, oh, it's 1/2 past. 1/2 what? No, it's 11:30, okay? Versus, my phone's in use. What's the actual time?
11:28. And there's also 11:29 according to my watch, but my watch is
11:28 and 54 seconds, right, is not only closer to the real number, it has more information in the answer than, it's 11:30. 11:30 is a soft answer. It doesn't contain the precision that it's 11:29 and 54 seconds includes. Okay. So this one is tied to reproducibility, because how do you get to trust your answer? You get to trust your answer because somewhere there's been a methodology that has been worked out that I can put this on a balance and weigh these first 3 digits in grams easily, and those last 2. And I've done this over and over and over, and I've calibrated. I've calibrated the balance, and I can trust that number. Accuracy's got nothing at all to do with precision, in the sense of they are independent of one another. Accuracy is how close is your answer to the real value. So if it's 11:30 and you are asked what time it is and you say it's 2:34 and 18 seconds, you've given me a precise answer. It contains lots of data. It is wildly inaccurate, because it's nowhere near what the real answer is. Okay? So these two get misused by the general public because they don't know the actual real definitions. They think it's the same thing. They get interchanged. What we're hoping for is our analysis gives us a number that is really close to the actual value, but also contains useful precision, to the point where it's still useful. Day one, we talked about measurement, that there are things that, like mass, we can't measure to the femtogram because there's nothing that small that can be measured. So you get the precision to a meaningful number. Okay? All right, so the days of you saying moles is mass divided by formula mass, plot this number on top of that number, put it into the calculator, find an answer. It's the last time you're ever going to do that. Because now we know that there's a limit to how much we can trust our numbers. And so every number is going to come with an error associated with it. It's going to come with an uncertainty. And every time we mention a number, we also have to mention how certain are you that that's the real number? If we use volumetric glassware, That's a volumetric flask. We brought in a burette on Thursday, didn't we? What was its number? Did anybody write down what its number was? I think it was a little bit larger than the 0.12 because it's incremental. It's got little increments. Let's go back and look at that. Volumetric flask. Not dispenses. Wrong word. Contains. 250 milliliters. Plus or minus 0.12 milliliters at 20 degrees Celsius. This is called our value, and this is its uncertainty. How do you want to spell burette? We've got two ways of spelling it. The American way or the French way. Two T's and an E. It's feminine.
The whole booty boy.
Yeah, well, we didn't
I'm
get
still
that
mad
far.
about that.
So we have a burette, and I'm going to start here. We brought one out the other day, didn't we? I'll go get another one. And do they read from the bottom up or the top down? Yeah, they read from the top down. So 0 is up here somewhere. 0 is the worst possible place to start a titration because there is no -1 or -0.1 on the burette. So you only get a line and there's incremental gradations below it, but there's nothing above it. So you're now one-dimensional with your error. Your volume errors are plus or minus a volume. And if you start at 0, you are depriving yourself of being able to visualize whether your error is a negative number. So always start your titration at any number at all, as long as it's not 0. All right, let's have this be seven. The bottom of the meniscus is exactly touching. And here's 8. And your new meniscus is there. The glassware allows you to see in increments of 0.1. So we know that that's 7 and this is 8, so that is 7.5, this is 7.6, 7.7, this is 7.8. But your meniscus is lower than the line. That meniscus is between the 7.8 and the 7.9. What you going to do about that? Ignore it?
No.
You guess. This is the only time where guessing improves your precision. Every time you move a liquid from one container to another, there's always an inefficiency. You always do something wrong. Every time you move a solid from one container to the other, you always leave something behind. There's always the chance of spilling. You always make an error. Every time you guess a number, you introduce a human error. But if I can tell that that's between 7 and 8, why don't I tell you that it's between 7 and 8? That it's, between 7.8 and 7.9 is what I meant to say. And I'm guessing that it's closer to 7.8 than it is to 7.9. So it's not 7.85. I'm going to make that be 7.83. Okay. How much was dispense? You go 7.83 minus 7.0 equals 0.83. These are in milliliters. So that's my answer. Except
Brief commercial break.
Get used to these.
Yes, it was.
Sometimes the commercial break is, let's go to lab and just do something. Doesn't get fun.
So long. At first, I thought it was gonna be like 50 minutes, and they kept on going. I was like, kept on looking at the time. I was like,
Tuesdays and Thursdays are an hour 15, typically.
the good thing being close to the office and close to the lab is we can just run away and get that. See that? What does it say?
To dispense at 20 degrees Celsius in milliliters. I don't know. I don't see the exact value.
Did I pick one that doesn't say it? Oh, good grief, I picked one with the rack that doesn't say it. Okay.
Just roll the credits.
Please breathe. Kat, is Dr. Hoffman teaching you cell microarray?
I switched out of solo. I have to do physics too.
Oh.
I wanted to take. I was so excited to do. I love biology. I love her. She's great. Yeah.
How's it going?
Okay. I'm doing better than I thought I would.
That's good.
At the moment. Still
Stop
not beginning.
calculus 2. That's the only class I'm worried about.
So far it's been chill.
So we're just pretty chill.
It's been reviewed so far.
Yeah. Have you watched the videos for anything?
I'm gonna watch it. Maybe after. Or probably later.
I'm inventing a number.
Okay. Great.
Okay. That number is probably good. This one, not so much.
Yeah.
So I'm gonna say to 0.1, and then have it be the same as this. Here's how uncertainty works. You look at the clock, and the clock says, and then you look at the clock again. And it says 9. How much time has elapsed?
We don't know. It's uncertain.
How could you not know? It's on the board. The big number minus the little number.
The clocks aren't precise enough to know how much time necessarily.
It's a digital clock. They paid a lot of money for it.
Put the seconds on it.
Oh. So, because there's no visible seconds here, and my least significant number. So significance isn't equal. This is more trusted than that. So as you go to the bigger number, it's more likely to be correct. This is the least precise number because it's the last one, and we don't have seconds. So the difference between 8:59 and 9, you look at it, you look away, you look back, that could have been a second. In fact, could it have been a millisecond?
Yes.
Yeah. Could it have been a full minute?
Yes.
It could have been.
Really?
Who knows?
I don't know.
If this is 8:59 and 1 second that we can't see, and then we don't look at it for a full minute, and when we look, will it read 9? Yeah. What's the longest that the interval could be?
60 seconds.
No.
Oh, wait. It could be 1 minute, 59
It
seconds.
could be 1 minute, 59 seconds between this and that. It could be basically it could be 2 minutes, or it could be a millisecond. That's how precision works. We don't know what that number is, therefore you have to account for it. The gap between here and here is plus or minus 1 minute and 59 seconds. Well, not plus or minus. The maximum gap could be 1 minute and 59 seconds. The smallest gap could be a nanosecond. All right? We don't know what that number is. We're uncertain of it. Okay. These are my values, that is my uncertainty. When I do the math, I get this number. Now I have to transpose the uncertainty to be plus or minus at the end. And the textbook tells us how to do that. On page 57. Because we have 2 rules. Well, 2 basic rules. Are we adding the numbers together, or are we multiplying or dividing? Okay. First, let's think about rules for significant figures.
They're between 2 numbers.
When you add or subtract, which is what we just did, of 2 values, and I'm subtracting one value from the other. How many significant figures were in this? 3. How many significant figures in there? There's some zeros in there. 3. There's some zeros.
But they're validated by the.
They're after a number and there's a decimal point. So they get to be validated. So I have 3 sig figs here, and I have 3 significant figures here. How many significant figures are allowed in my answer?
3.
How many have I got? So what should I do? Do I add a 0 to the end? Like here?
But we don't know.
We do know, because you're misapplying the rule. The rule that says if you have 3 significant figures here and you have 3 significant figures here, you're allowed 3 significant figures in your answer. That's for multiplication and division. The rules for addition and subtraction were different. When you add or subtract, your answer can contain the same number of decimal places, not significant figures,
Forgot about that.
as the least precise value. Okay. So, these both had 3 significant figures. They both had two decimal places. And so the rule for my answer is not that my answer gets 3 significant figures, it's that it gets 2 decimal places. Because the trouble with adding and subtracting numbers is you can kind of invent fake precision if you follow the rules for multiplying and dividing. Okay? So if I multiply or divide, the rule is that the answer contains the same number of sig figs as the least precise value in the question. So, I need two things. I need to take this number and subtract that number from it to get this, and I need to use the rules from significant figures for the correct application, right? I've done an addition or a subtraction, I use this rule, multiplication or division, this one. Okay, the way that we take care of the error is this. It's a very small board in this room. It's called propagation, propagation of errors. And there's a table on page 57, and that table contains, hey, if you multiply or divide numbers, this is how you propagate the uncertainty in that number. If you add or subtract them, this is how you do it. And if you take the log of a value, this is how you do it. And if you take the exponents or the square root, this is what it looks like. So we need a table with a handful of mathematical conversions in it. And then that will let us know how much I can trust this. Okay. So the big two are addition and subtraction. And multiplication and division. When you add or subtract, the error, the uncertainty in the answer is equal to the square root of the error in the first number squared plus the error in the second number squared. Our book calls this y, and these ones x. So these are the uncertainty in each value. Okay, so let's do that. This value right here is my uncertainty. In the answer. And it is equal to 0.12 squared plus 0.12 squared, and then you take the root of it. We all need to know how to do this on our calculator. Did you bring a calculator? We should practice doing. People still put the 2 here, tell you that it's the square root.
No.
I guess not.
Like I've seen it before, so it's something like you're gonna do that for this cube root.
Mhm.
And then, I'll just.
It's kind of redundant. 0.12 times 0.12 is 0.144.
0.01.
Zero, yeah, 144.
Yeah,
Because 12 times 12, it's 144.
that's gross.
It's gross.
Gross.
Yeah, no, that's the actual way. we're
And
supposed to do it.
because it's in the 10th, it's already a number that is less than 1. When you multiply it, you're not really making the number bigger, you're making the number be smaller. Yeah. And then at that,
Mhm.
so you got 2 gross.
No.
So 0.0244.
288.
288, there you go. I'm doing it in my head. And then what's the square root of that?
I got 0.169, but that, well, 0.170 if we're doing, but we're not gonna do the third. I hate 6.
I know.
Okay. No, we'll talk about this. because your calculator is going to give you a stream of numbers, and oh, it's got more.
Yeah.
6970.
0.5.
All right.
Yeah.
Question is, where do we round that number? Do we trust this?
Yes.
We trust that number.
Yes.
Do we trust this number?
Mostly yes. Yes.
Yeah. Yeah. Do we trust that number?
No.
Not so much, because that's the number with the plus or minus in it. Not this one. Not that one. If the plus or minus part happened here, I wouldn't have written the 3. Okay, so our uncertainty starts at that number. So we don't need that. If you multiply or divide, it's a little bit different. This number, this is a measured value, right? This is the deal. That has been measured, which means this, it's an E, it's an error, but this is the original one. This is the start point for your error. So this is what we call the absolute uncertainty. We didn't have uncertainty before we made the measurement. The uncertainty arises because we made the measurement. And if we'd have measured it with a beaker, it would be a different number. But we measured it with the burette, and we can use this teeny number instead. Okay? All right. When you multiply or divide, we're going to do something different. And it's the same in both cases. We get the percent error. And the percent error is equal, I have to remove that, to the percent error in the first measurement squared plus the percent error in the second measurement squared.
How do we find the percent error?
It can either be written at the source, or you can figure it out. But that times that. Okay? So let's think about times when we would multiply two numbers together in chemistry, from general chemistry. Go. There you go. M1V1 equals M2V2. Or moles is mass divided by formula mass. And we could pretend, we could round up the formula mass to be a certain number of digits, because they will go on. Some of them will have formula masses on the periodic table with like 5 decimal places. What if I rounded it to 2? Then I would have uncertainty in that third digit. That could be plus or minus 5 at that third decimal place. And a mass on a balance could be at the second decimal, could be at the third decimal. Or I've got molarity that I'm uncertain about, and a volume that I'm uncertain about. If I do M1V1 equals M2V2, then I have to find, let's say I have to find V2. That's M1V1, there's an M1 and a V1 and an M2. So I'm multiplying something and dividing something. That gives me 3 terms. We'll do those on Thursday. Let's see if I can find a nice easy one. Didn't book give me a nice easy one. It's a physics question, but it might do. Let's see if there's a question in the back of the book that would be better. Or I could just make some numbers up and say pretend. Okay. Here we go. This is 3:15 from the book. It doesn't tell you what these quantities are. Question 9.43. Plus or minus 0.05 multiplied by 0.016 plus or minus 0.001. Okay. So this question is 2 values that you are going to multiply by each other, and 2 absolute uncertainties that we have to convert into percentage uncertainties. Okay? So, first, how many significant figures is this?
3.
How many significant figures is that?
4. No. 3. 4. 2. Oh.
The 0 has to be sandwiched between 2 numbers, or after a number that includes a decimal place. Those zeros are before the first real number. Only 2 significant figures here. How many significant figures am I allowed in my answer? 2. Because I'm multiplying or or dividing. The product in this question is only allowed to have the same precision as the least precise piece of data that generated the answer. Okay? So first of all, go ahead and multiply those together. Give me the whole stream of numbers.
0.4715.
Okay. I'm not allowed to have those. I am limited to 2 significant figures. Okay. That's the value.
Oh, wait,
Hold up.
sorry, I thought you meant per section, my bad, I didn't do the whole thing, multiply.
The whole thing would be 0.15.
Oh, 0.1.
Sorry.
5088.
Say again.
5088.
Okay. You're not allowed to have those. Limited to 2 significant figures. Alright, yeah, that looks better. Alright, B. I'm gonna convert absolute 2% error, which is E over X times 100. You put the error over the value. So my error is 0.05 divided by 9.43 multiplied by 100.
When we give the answer for that one, we give as many, do we give 2 decimal places?
Let's see what it comes out like. What's your number? So what I'm going to do is I'm going to use everything that the calculator tells me in the question. I'm just not going to admit it to the person reading. Okay. So 0.05 divided by 9.43 times 100 equals 0.1.
53.
Let's have that be. Technically, I've only got that one significant figure here. If we use the rules for significant figures in the calculation, I am stuck here. But if I round up in the middle of my equation, I'm doing something very, very foolish. Do not round up until the end. So you only admit this, but you use all those numbers. Okay, and the bottom one?
6.25.
And these are percentages. And here again, technically I'm limited because only one significant figure went in. So is that really just 6%? That might be the only thing that I admit to on paper, but am I including these numbers in my calculation? For sure I am. Okay, so now C is the percent error. And the percent error is 0.53 squared plus 6.25 squared. Take the square root of it. That will give you an error in the percentage, which if you wanted to, you could switch back to being an absolute value, because we also know what the product value is. Did it really go up? Okay. I wasn't expecting it to go up. I don't know what the real number is. What's your number?
5.86, but I'm also using my phone.
I've like all I put like the 0.53 or blah 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 and put the 6.25 blah blah the full numbers.
Mm-hmm.
I'm just gonna put
And you squared them both?
Yes.
Okay. I did think it was going to be smaller than the answer that you gave me, but that doesn't mean anything. It's just like that's what I was expecting.
Wait, hold up, what number did you get again, Kat?
I got 6.27.
Okay, same, I'm.
There you go. Now, if we wanted to, so the final answer is when you multiply this by this, the answer is 0.15 plus or minus 6.3%. Okay, what is 6.3% of 0.15? Because if the next thing that I do to this is add it or subtract it from another number, I want that to be an absolute error now, not a percent error. So let's go ahead and switch this back to being an absolute number. And we do this, that's 6.3 divided by 100, that's what percent means, multiplied by 0.15 equals 6. Keep your big numbers in. 6.27 or whatever it was divided by 100, multiplied by the 0.15, and if you want to include all of the decimals in that one. Keep all of your precision in until you are asked not to leave it in any longer. Only round up at the very end. If you round up multiple times during a calculation, you will find that your answer has drifted. It's nowhere near where it should be. What does this come out to be?
0.009405.
0.009. Okay. Let's look. I have certainty at the first decimal. I have the beginning of uncertainty at my second decimal. So I'm going to take that 9 and round it up and make this be. That's my answer.
This is another question I forgot, but why for the 6.3 over 100 do we have to multiply it by 0.15?
Because that was the answer. But 9.43 multiplied by 0.016 was equal to 0.15. Plus or minus 6.5%. So what is 6.5% of your value? This is your value, that's your error. This is my value, that's my percent error. This is my value, this is my absolute error, or absolute uncertainty. Okay? All right, see you Thursday. Thursday, we can do a couple of these. But we're also going to start saying, you know, if you want to trust your results, you have to do them again and again and again and again. You do them in replicates. How do I know if I have an outlier? How do I recognize that there's an outlier, and then how do I throw it away? Statistics, starting on Thursday.